All right, good morning, class. Welcome to this lesson on Electrostatics 5, electric fields, the math portion of it. Today, we will be able to define the electric field equation and set up some common electric field problems. So, um, let's go back to our discussion of what an electric field is. Okay, so we have a situation right here. We have a positive sphere, we have a negative sphere, we have a negative rod, and we have this test charge here, this test charge. So this sphere is sending out electric field lines in all directions out. This one is taking them all in. And this one's also going to be pulling it in because it's also negative. If we take all these electric fields into account from these three things, this test charge will have a force on it in this direction, okay? Because this one's pushing it away, this one's pulling it in, this one's pulling it in. And so if we take all these in, it's going to have a force in this direction. And this test charge is so small, it won't affect the field. It won't affect the field. Okay, so it has a charge, but basically this charge isn't going to affect these three things. These are so strong, this test charge won't matter at all. So our equation for this is going to be an electric field, and this is going to be a vector, is equal to the force divided by the test charge. Okay, so Q0, this is the test charge. So this is going to be our equation for an electric field. Basically, we have the force equation, and we divide by the test charge because that basically cancels out. That basically cancels out the test charge because the test charge doesn't matter in the electric field. The electric field is so strong, this is negligible, so we just divide by it. So if we want to know the force in an electric field, all we have to do is multiply both sides by the test charge, and we get this equation right here. So these two equations are synonymous, okay? And the unit for an electric field is simply newtons per coulomb. Okay, there's no name for it, it's just this, okay? So an electric field is very similar to force, except we divide by the test charge because we're canceling it out. It's not going to affect the overall field. So we have an electric field of newtons per coulomb, and we can also break it down to this equation right here. So what does that look like? Let's take another look at this, okay? We have the same exact situation. We have right here, we have positive sphere, negative rod. Okay, on this positive test charge, the force is going to be in the up direction, which is what we saw in the last slide. And the electric field is also going to be pushing it in this direction along the lines of the force. So electric field and the force are the same when the charge, or when Q0 is positive, because if you notice here, we have always assumed the electric field. We have assumed the electric field is for a positive test charge. What if the test charge was negative? What if the charge was negative? Well, the force now is going to be in the opposite direction because this one's going to push it away, this one's going to push it away, this one's going to gather it near it. So it's going to be in the opposite direction, despite the fact that the field is in the same direction. The field doesn't change, and that's what I'm trying to get at in these videos. The field does not change. The field is not affected by the test charge. The field is going to be in this direction. We assume the field is for a positive charge. Okay, that's by convention. It makes everything the same. It makes everything simpler, despite what you may think. But even if we have a negative charge in here, the force is going to push it in this direction, but the electric field is going to be in that direction. Okay, so the electric field does not change based on the charge. The force does. The force changes based on the charge, but the electric field always stays the same. Okay? So we have some common examples here. We have two electric fields. We have electric field from A, electric field from B. So what's going to be the electric field at point P? Well, the electric field is a vector, which is what the symbol denotes right here. So just like with forces, it's all the same thing. We would calculate the electric field at this point right here. We move it down. this point right here, move it over. So at this from point A, there would be an electric field forcing it this direction. From point B, it'd be in the downward direction. So the overall electric field would be the resultant of these two. So we have to do some trigonometry just like we do with forces, okay? So electric fields and forces are very similar. Electric fields and forces are very similar, okay? So we treat them kind of the same way, except one we divide by the charge and one we don't. Another common example is an example like this, and this example we have two charges here, Q and Q. These have their own fields, and the question might be something like, where is the electric field? Where is the electric field equal to zero? Okay, where is electric field equal to zero? Or, um, and from looking at this electric field is going to push on point A in this direction. This electric field is going to push on this point in this direction. So overall, the electric field at this point is going to be zero. Versus over here, 2D and 3D is going to push them both further away. Okay, so there's going to actually be a positive field here that's further away. So these are just some common examples of electric fields, and you're going to see a lot of examples like this. You're going to see a lot of examples like this, where we have in a line, where we have things in a square, or in a triangle, just like I talked about with forces, okay? Like I said, forces and electric fields are very similar. It's just one we divide by charge and one we don't. And so also, our last note here is going to be electric field equals force over Q0. Well, we can, depending on the question, if F equals K Q1 Q2 over R squared, and this is all over Q0, well, we can assume, if Q2 is our test charge, then this is just Q0, and so these two cancels out. So our electric field equation can possibly be simplified into this. And this Q1, for example, this Q1 would be like the Q1 right here. We would call that Q1. And so what would be electric field due to this whole thing right here?